Hello, Chem 1132. This is Mr. Koker. Just wanted to do this video with you to take care of Monday's class because of the eclipse and all the traffic. The powers that be at Frontier decided that we would make today a remote class. So I'll jump right into the lesson and we'll do the video, and I might do this video in multiple videos. Going for a couple hours might take a while, so better than doing it straight through might be to break it up a little bit, but we'll see how it goes. So to remind you what we are talking about, we are in the section on electrochemistry where we talk about how electricity can impact chemistry, how you can use electricity to make chemistry happen, but also how chemistry can produce electricity. If you think about a battery is a chemical reaction that produces electricity. So the type of chemical reactions that we study in electrochemistry are redox reactions. So redox reactions are where you have two chemicals. One is reduced and the other is oxidized. One is reduced by gaining electrons, the other is oxidized by losing electrons. So thinking back to last Tuesday, we learned how to balance redox reactions by breaking them into two half reactions, balancing the non-hydrogen and oxygen elements, then balancing the hydrogen and oxygen using H plus and H2O, and then balancing the charge using electrons, then figuring out how many times the oxidation and the reduction reaction have to go in order to have equal number of electrons transferred for both half reactions, then put it back together, simplify it, and you've got a balanced equation. So that's a lot of steps, but they're outlined on here, and we went through a couple examples in the notes, and you can practice those. Also, there probably are some in the homework that you can practice. We also learned that for a basic solution, it adds a couple of steps. You have to take your H plus ions and add OH minuses to both sides to neutralize the H pluses and produce waters, and then cancel the waters out on both sides until you get down to the simplest number of waters. So you can go back through the notes and see these examples that we did. For acid solutions, we use H plus and H2O. For base solutions, we still use H plus and H2O, but when we are done at the end, we convert our H pluses to waters using OH minuses on both sides, and then eliminate the waters on both sides that are redundant. And then we have our final balanced equation that has OH minus in it for base solutions instead of H pluses, which would be appropriate for acid solutions. Okay, so that was all learning how to balance redox reactions, because we eventually want to apply that to these arrangements of oxidation and reduction reactions that will produce an electric current. So these are called galvanic cells. Galvanic cells. And it's plural because they always come in pairs. So a galvanic cell is a device which chemical energy is converted into electrical energy. So you think of a battery. A battery is an example of a galvanic cell. So the way a galvanic cell works is it uses a spontaneous redox reaction. Remember, a spontaneous reaction will have a negative delta G, and it's capable of doing work. The kind of work that we're going to use with these spontaneous redox reactions is the kind of work you can do using electricity. So we use electricity to run a motor, or use electricity to drive an electric vehicle, an EV. So that's an example of getting useful work out of a chemical reaction. So as our first example of a chemical reaction that might be able to be harnessed to do work would be this reaction between permanganate ion, MnO4- and iron plus 2. Now, if this is run in an acid solution, the balanced redox reaction would be 8H pluses plus MnO4 minus plus 5Fe plus 2s will make Mn plus 2 plus 5Fe plus 3s plus 4 waters. Now, if you look at the iron changes from plus 2 to plus 3, so that's being oxidized. And it's actually the MnO4 minus converting to Mn plus 2 that is the reduction step. So we break them into their half reactions. This is what it would look like. The permanganate is adding 5 electrons being reduced by the addition of 5 negative charges to produce the Mn plus 2. And then the iron plus 2 is losing electron to become plus 3. So it's loss of electrons. It's called oxidation. Now, because the reduction step involves 5 electrons and the oxidation step only involves 1, then we have to multiply the oxidation step by 5 and then put them back together to produce this balanced equation that we showed you on the previous slide. 5Fe plus 2s. Now, if you put permanganate and iron plus 2 together in a beaker in the same solution, the electrons are just going to transfer directly from one chemical to the other. That's not going to get you any useful work. Instead, what you want to do is to keep the reduction half reaction separate from the oxidation half reaction. And then if you find a way to connect the two solutions with a wire, let's say, the electrons that want to flow out of the oxidation reaction as produced by the oxidation reaction into the reduction reaction will have to flow through that wire. And that's where you're going to be able to harness the work, because electrons flowing through a wire, that's electricity. Electricity is simply the flow of electrons through a wire, and we have techniques where we can harness that. We can light light bulbs with it. We can drive an electric motor with it. So we can run our computers and our cell phones with it. It's the idea of a battery producing an electric current. So this would be a schematic of what you might arrange for this particular reaction. So on the left we have the permanganate MnO4 minus ion and the H plus, because those are the two reactants in the reduction step. And on the right we have the Fe plus 2, which can potentially convert into Fe plus 3 on the right. So we have our reactants ready, and so then you'd have some metal connecting the two sides, metal electrodes, metal wire, and then the electron would flow, since it's being produced by the oxidation step. It would flow from the iron side over to the permanganate side, because it's being used in the purple solution, the permanganate. It's being produced in the green solution, the iron plus 2. So the idea would be that the electrons would flow through the wire, and that then if you put something in between on that wire, you could get some electricity to do something for you, whatever you can get out of an electric current. Now, before we move on to a further discussion of this chemical arrangement, we need to get some vocabulary down. So if you may have heard this before about electrodes, that electrodes can be positive and negative, and also that when you have a positive and negative electrode, that they have the name anode and cathode. So anode is one type of electrode, cathode is another type of electrode. Now these prefixes have been used before in chemistry here. We've called negative ions anions, and we've called positive ions cations. Excuse me, sorry about the cough. So we've used these prefixes before, and you know that they stand for different kinds of charge. Now, to define for a galvanic cell what we mean by an anode is where oxidation occurs. So the oxidation reaction in this particular arrangement we've talked about is the iron side. So in this particular schematic, the iron, the green side, would be the anode. That metal electrode hanging in the solution would be called the anode. And reduction always occurs at a cathode. And so the cathode would be the purple side. So the electrode on the purple side would be called the cathode. Those are two different names for two different kinds of electrodes. So an electrode where you see oxidation occurring is called an anode, and an electrode where you see reduction occurring is called a cathode. Now, there's a funny way of remembering which is which, and that is to imprint on your brain two mental images. So look at this picture on the left. That picture on the left is a picture of an ox. An ox. Anode, oxidation. An ox. So every time you think about, which is which, anode or cathode, an ox, because ox starts with a vowel, you have to use the an instead of a. You don't say a ox, you say an ox. So if I think of the picture of the ox, and then I think ox means oxidation, then an ox would mean anode is the oxidation side. Now, the other one is kind of an absurd picture because you normally don't see cats this color, but you imagine in your mind a red colored cat. A red cat. Reduction occurs at the cathode. Red cat. So an ox, anode, oxidation, red cat, reduction, cathode. So typically with these two different anode and cathode side, that's going to allow electrons to flow through that wire. Now the problem is when electrons flow through that wire, you would end up building up charge on one side or the other. You'd build up negative on one side and positive on the other. And eventually that charge would, and this would actually happen very quickly, that charge would then start opposing and pushing back against the electrons that want to flow. So the electrons, maybe they flow from right to left here, but then electrons build up on the purple side, and they're going to repel the electrons that want to keep flowing through the wire. And so you might get a very short amount of current, and then it would have to stop because you probably learned even in elementary school that for electricity to work, it has to complete all the way through a cycle. And here we simply have a flow of electrons from right to left. There's no way for the electrons or the negative charge to finish the circuit. So this is an open circuit, and you know that you can't get electric current to keep flowing in an open circuit. However, what you can do in this particular case is to add something called a salt bridge or a porous disc. So these are devices, two possible devices that will allow ions, which do have electric charge, to flow between the two solutions. So you're not really mixing the solutions, but you have ions migrating from one beaker into the other. And so up in the wire, you have electrons flowing, but between the two solutions, you connect them in a way that lets ions finish the circuit. And so this finishing of the circuit allows continual flow of electrons. the electrons flow through the wire, then ions flow from one beaker into the other. And the flow of electrons finishes, or the flow of ions rather, finishes the circuit. And so you don't have an open circuit, you do have a completed circuit. So a salt bridge would simply be like a U-shaped tube that would be filled with a very strong electrolyte, something with a lot of ions in it. And the ions might be held in some kind of jello-like matrix where it doesn't just pour out of the U-tube. They're sort of suspended but able to move if the electrical pressure pushes them from one side to the other through this jello-like matrix. Or a porous disc can actually just be a connection between the two beakers, where the beakers are maybe all they have between them is simply a disc with little holes in it that the ions can flow through. So this would be a picture of what that might look like. So you see we've still got our electrodes and we got our two beakers, but on the left we see a salt bridge, and inside this tube connecting the two in a U shape is something with a lot of ions, a very strong electrolyte in like a jello matrix. And then on the right, an alternative to the salt bridge idea would be some kind of disc that would have holes in it that would let ions through, but it wouldn't let like fast flow and fast mixing. It would only just let the ions flow. So maybe if it were similar to this previous picture, maybe the right side would be electrons flowing, but then the salt bridge might be negative ions flowing from left to right. So electrons would flow from right to left, but then the negative charge would be continued through the circuit by negative ions flowing into the right beaker, or alternatively, or along with, positive ions flowing into the left beaker. So the movement of positive ions to the left would be the same as the movement of negative ions to the right. And this can happen either in the salt bridge or from one beaker to the other through the porous disc. So you have to have these for this galvanic cell to work and able to produce electricity, because without it, you've got an open circuit. You have to have something that completes the circuit. So galvanic cells are going to consist of an oxidizing agent in one compartment, and that oxidizing agent, remember, oxidizing agent causes something else to be reduced. So it's going to pull electrons through the wire from the reducing agent in the other compartment. So in this case, we're seeing the permanganate MnO4 minus is where reduction is occurring, but that means MnO4 minus is an oxidizing agent. It's going to pull electrons from the right side over to the left, or you could look at it as Fe+2 pushing electrons over to the left. But the oxidizing agent is going to be getting electrons from the reducing agent, which is the iron +2. Now, every combination of two half reactions, one half reaction where there's an oxidation taking place and the other half reaction where there's reduction taking place, every one of those is going to have a ability to move electrons. And in physics, you learn that electrons move due to electric potential. So it's sort of like potential energy. Very often electricity is described as similar to water flowing downhill. Electrons flow downhill, not gravity downhill, but in the direction where they go from higher potential energy to lower. And that's how they're able to actually transfer some of that potential energy to something like a motor or a battery. They're able to give it energy because the potential energy of the electrons lowers when it goes from one half cell. We call each side a half cell. When it goes from one half cell to the other, when the electrons move from one side to the other, they're actually, by analogy, it's as if it's like water flowing downhill. So we call it a cell potential. And it has to do with sort of the force that's moving the electrons through the wire. It's also known as the electromotive force, if you're thinking in terms of physics, which is, a physicist would abbreviate that, the EMF, the electromotive force. And it's measured in units that you've probably heard of called volts. Think of like the voltage of a battery. You know, a double A is 1.5 volts. You have a 9-volt battery. So we have these voltages that are like the degree of push and pull that the electrons feel that pushes and pulls them through the wire. Now, the relationship between the unit in physics called the volt and the work that can be done by the electrons is that a volt of electromotive force, 1 volt, is capable of doing a joule of work if a coulomb of electric charge is moved from one side to the other. So it does a joule of work, joule is an energy unit, for a coulomb of charge. A coulomb is a charge unit. Now, coulomb is probably less familiar right now than joule, but just to kind of remind you back to the very beginning of the first semester, we talked about the electron charge being measured in the Millikan oil drop experiment. And it was measured to be 1.6 times 10 to the minus 19 coulombs. Well, coulombs is a measure of electric charge. So a joule per coulomb is the same as saying 1 volt. So the volt is sort of like, you know, how big of a hill, potential energy hill, is the water flowing down. The taller the hill or the taller the dam of holding back the water, the more energy you can get from the water when you release it to go to the other side of the dam. Well, in a similar way, we've got these electrons that are wanting to move through the wire and like water flowing downhill. And to say that the voltage from one side to the other is 1 volt is to say that you can do a joule of work if you transfer a coulomb of electric charge in the form of electrons. Okay, so thinking in terms of voltage, this brings up a standard set of voltages that can be associated with each half cell. See, a battery's voltage is going to be based on what is the chemical reaction in the left beaker and what is the chemical action in the right beaker. Thinking back to these 2 beakers, you know, that we have these pictures of, these 2 half cells. So each half cell has a numerical voltage value that's associated with it. And these values are called standard reduction potentials. So we have a chart of the standard reduction potentials that is associated with each chemical reaction, each redox reaction that might be occurring in one of these batteries. Now, this particular chart right here would be one that you would want to keep a copy of or know where to find it in your notes, and also to maybe use a copy out of the book. But this particular chart is a very important chart that we refer to in this chapter on electrochemistry. So it's kind of like using the back of the book for the appendix to get delta G's and delta H's, but this is for finding the voltage of a particular battery. So to get the voltage of a particular battery, we need the voltage that is, or the the standard reduction potential measured in volts for each side of the battery, so we know how far we're dropping downhill when we move electrons from one side to the other. So these chemical reactions, if you notice, all have electrons on the left side, so they are all reduction reactions. And each of these reduction reactions is associated with a particular voltage. Now, that doesn't mean that we only run reduction reactions, because for redox to work, you have to have a reduction reaction and an oxidation reaction. But an oxidation reaction simply means that we would flip one of these reactions and run it the opposite way. And so to get the two reactions that are going to be happening, for example, permanganate and H plus reacting on one side, Fe plus 2 and Fe plus 3 on the other side, what we would do is we would look up those reactions in this table. So if you go to the left side and go down about 8 or 9 rows, you see MnO4 minus plus H plus 8H plus 5 electrons yields Mn plus 2 plus 4 waters, and it has an associated standard reduction potential for that reaction of 1.51 volts. Now the other reaction is the Fe plus 2, Fe plus 3 reaction. Now it's about 4 or 5 rows up from the bottom left. So if you look in the bottom left of this chart and go up about 5 rows, you see Fe plus 3 plus an electron yields Fe plus 2, 0.77 volts. But that reaction is actually written backwards from the way we want to use it. See, it's got Fe plus 3 on the left and Fe plus 2 on the right. Going back here, we want Fe plus 2 making Fe plus 3. We want an oxidation reaction. This chart is only showing reduction reactions. But a reduction reaction, if you flip it, is going to be an oxidation reaction. So what we have here is the two reactions. We just have to simply take the Fe plus 2, Fe plus 3 reaction and flip it. And since it has one electron, remember, you got to multiply that one by 5 to get the same number of electrons as the MnO4 minus 8H plus 5 electron reaction. So that's how we might start out using this table, is finding the two half reactions, the half reaction that's occurring in the left beaker that is either making or using electrons, and then the half reaction in the other side of the two half cells. And then we simply take our two half cells, we connect them with a wire for electrons to flow from one side to the other, and we also add the salt bridge or the porous disc so we can complete the circuit and not have an open circuit. So this is all a lot of information thrown at you real quick, but it's a description of how an oxidation reaction paired with appropriate reduction reaction can create an electric current through a wire, and then all you have to do is splice in a calculator or a cell phone or a power drill or a electric vehicle or whatever you want to power using this electrical battery, so that a chemical reaction, a spontaneous redox reaction, can power something electrically. Okay, so we have our table of half reactions, and these are all written in the reduction direction. And this table, these values on this table are called standard reduction potentials. Their symbol is the scripted E with a standard symbol. Remember, the little circle means standard conditions. But this table is used over and over again throughout this chapter, in order to determine the voltage of a battery. That's the main use for it. Because a battery is going to be a combination of two half reactions. A left side beaker reaction where maybe oxidation or reduction is occurring, and then a right side beaker reaction where the opposite's occurring. If you got oxidation on the left, you'll have to have reduction on the right. But those redox reactions, because they produce and use electrons, you can force electrons to flow from one side to the other through the wire. Now, what voltage will that generate? Will it generate 1.5 volts like a AA battery, or is it going to generate a higher or lower voltage than that? Well, that depends on what you choose as your two reactions, because this table gives you a set of reduction reactions, which you can also choose one of the two to reverse, and that will produce you both a reduction for one and an oxidation. Because any of these reactions flipped around so that the products become the reactants, reactants become the products, converts to be in an oxidation reaction. We just chose to list them all in the reduction direction. That's why they call it standard reduction potentials. Standard because it's E naught, E and that circle sign. Reduction because every one of these reactions is written in the reduction direction, but they don't have to stay that way. You can flip them and make them oxidation, but they're just, the table is simply in the form of reduction. Potentials because the unit in physics for the amount of potential is a volt, and that's because these numbers all have units of volts, V-O-L-T. All right, so how do we use these to determine the voltage of a particular combination of two of these reactions? Well, first of all, let's address the issue of them being standard. Standard simply means that if you have any solutions for either half reaction, that the solute that's dissolved to make the ions in that solution needs to be 1 mole per liter. 1 molar is the standard condition for any aqueous solution. Also, occasionally these are going to be in the gas state. I'm looking at the left side about 10 or 12 rows down. It says Cl2 plus 2 electrons yields 2 Cl minus. Well, Cl2 is actually a gas. And so the standard state for a Cl2 gas would be 1 atmosphere of pressure of Cl2 gas. Now on the right side you have Cl minus. The standard state of Cl minus would be 1 mole per liter, or 1 molar. If you have any solids involved in the reactions, the standard state for a solid is simply the solid. You don't have to worry about a concentration unit or a pressure, because a pure solid, say you have gold metal, pure gold metal would be the state of that would be standard. Now, as you can tell, 2 beakers always, right? So that means 2 different reactions. You got one reaction occurring in one beaker, a different reaction occurring in the other beaker. So to get you the voltage of that particular galvanic cell, or basically battery, you would have to combine the standard reduction potential, the E naught, from each half reaction. So combining the 2 half reactions to get a balanced redox reaction requires a couple of manipulations. One of the half reactions will have to be reversed. So if we think about it, an ox, the anode will have to be reversed, because an ox The anode is where oxidation occurs. Remember, these are written as reduction potentials. So oxidation would involve flipping one of these two, or one of the two reactions. So you take a reaction from this and you flip it, and that turns it into the oxidation step. Your reduction step, you run the regular way it's written in the table. The oxidation step, you pick one of these reactions and you flip it. So then, if you want to know how much voltage combining those two reactions would create, in other words, what is the voltage of the battery I make if I use this one as my reduction step and this other one as my oxidation step? Remember, reduction, cathode, red cat, anode, oxidation. So the particular half reaction that you choose to be a reduction step, you would find the voltage on this chart, and then from it you would subtract the voltage for the reaction you chose to run in reverse as your oxidation half reaction. And so E naught of the cathode, where reduction is occurring, minus E naught of the anode, where you're flipping the reaction and running it as an oxidation reaction, anox. The difference between those two numbers is E naught cell, or the voltage you would generate if everything was in standard state, 1 molar for all the ions, 1 atmosphere for all the gases, all the solids in the solid state. Like these solid electrodes, they would need, these pieces of metal would need to be in the solid state. So by taking one half reaction and running it in one beaker, calling it the cathode, and that's where the reduction is occurring, and the other reaction being the anode, and where the oxidation is occurring, because we're flipping one of these two half reactions. If we take the value on that table for the cathode step minus the value on the table for the anode step. See, reversing the anode means we're subtracting it because we're changing the sign of E naught. But the combination of E naught of the cathode minus E naught of the anode gives you the voltage that that particular battery or pair of two half cells would generate, how much voltage you would get from it. Now, the other manipulation is that you have to multiply the cathode or the anode by some numbers to get the number of electrons to come out correct. So if you think back to this reaction, we had to multiply the iron side by 5 so that 5 electrons could be produced on the oxidation step, the anode, and then transferred over to the reduction side, the cathode, through the wire, so that the cathode could be where 5 electrons were used. But you have to be able to move the same number of electrons from one side to the other. You can't send 4 and expect 5 to arrive. You got to send 5 so 5 can get there. Now, about multiplying it. Your intuition might say, oh, if we multiply it, then we have to multiply the voltage, because we would do that if it were thermodynamics and we were doing delta H or delta G. But that's not true. Just because you're sending more electrons doesn't mean you're changing the height of the hill that those electrons are flowing down. The value of E naught of the cell does not change. We still take the number straight from the chart for the cathode side minus the number straight for this chart from the chart for the anode side. We don't multiply it by 5 if you're running the reaction 5 times. Do not multiply the E naught values. Simply take them straight off of this chart. Take one number off this chart for the cathode side, take another off the chart for the reaction you're flipping around and calling the oxidation step, take that number off the chart, and then take the number for the cathode minus the number for the anode. Now you may recall that we say that we run spontaneous reactions. Spontaneous reactions want to go one direction, they do not want to go in reverse. Like a ball rolling down a hill doesn't want to roll up the hill. It just wants to roll down. So in a similar way, there is a way to choose which half reaction to make your reduction and which half reaction to make your oxidation, which half reaction to do at the cathode, which half reaction to do at the anode. So this is one of the most important things I'm saying right now. Right now, listen closely. The cathode needs to be the number with the higher voltage. If we look at these E0 values, we notice that they start at 2.87 for the F2 plus 2 electrons yield 2 F minus, and go all the way down to negative 3.05 for the lithium plus 1 plus electron makes lithium. So think of it like a number line that runs from positive 2.87 to negative 3.05. That means that my reduction reaction, my cathode reaction, red cat, the side that where electrons are going to be used to reduce some chemicals in the solution, needs to be the one that is higher in E0 value, the one that is the more closer to the positive side or further along on the positive side of the number line. And then the one that is lower in E0 value will be the one that you choose to make the anode side. And you will flip the reaction and run it in reverse, and that will be the anode side. And so the anode always bends a knee or gives in to the cathode. The cathode is stronger. It's got a higher E0. So it makes it stronger than the lower E0 value. So the one that we decide to flip and let be the oxidation reaction is the one that has a lower E0. And then to find what voltage that combination of two half reactions, that reduction and oxidation reaction, will give you, you simply take the two numbers on the number line and take the higher number minus the lower. I like to think of it as simply how far apart are these two numbers on the number line. If I pick the first two, F2 plus 2 electrons makes 2F minus. And I decide to call that my cathode. And then I pick the one right below it, Ag plus 2 plus electron yields Ag plus. Well, I can't have two reduction reactions. So I take the second one, since it's lower on the number line, and I flip it. I say, oh, I could react F2 with Ag plus. F2 on the left of the first reaction, Ag plus on the right of the second reaction. I could flip it and make it on the left. So now I could have Fe plus F2 plus Ag plus could give me Ag plus 2 plus F minus. Now I'd have to run the second reaction twice, but that wouldn't change the 1.99 number. It's still 1.99. I simply run it twice to balance the number of electrons. So then, since I'm running the first one forward, but I'm running the second one in reverse, I would have my two half reactions that could happen on the two different sides. Got my F2 on the one side reacting with the Ag plus on the other side reacting. So then I could expect the voltage from that to be the difference between 2.87, the cathode, minus 1.99, the anode, or a difference of 0.88 volts. So if everything was standard, if the F2 was 1 atmosphere, the F minus was 1 molar, the Ag plus 2 was 1 molar, and the Ag plus 1 was 1 molar, and everything was done at 25 degrees Celsius, standard conditions, I could expect, pairing these two reactions, the first one in the forward direction, the second one in the reverse direction, first one reduction, second one oxidation, that pair of two half reactions set up with a wire letting electrons flow from one side to the other, from the anode side where oxidation is occurring and the reaction is losing electrons. The electrons lost would flow through the wire to the cathode side where electrons are used to reduce something. And if I connected it with a wire and used the right electrodes and the right solutions and included a salt bridge or a porous disc so I didn't have an open circuit, then I could expect that combination of these first two reactions, going the wrong way, that combination of those first two reactions in the chart, that combination would give me 0.88 volts. But I can pick any two reactions off this chart. Any two reactions is going to have a difference between their numbers. And the amount of difference is the voltage you would create. If you let the reaction that has a higher number be the cathode, and then you reversed the lower number reaction and made it your anode, because anode oxidation. So a little complicated. Feel free to email me a question about it if it's not sinking in. I know this is a little bit of an awkward way to learn because I can't stop and ask you questions to see if you're understanding me. But I'm trying to over explain how you would use this chart. So I may be saying the same thing a few times. You're welcome to speed me up or slow me down to try to catch it. But it's very important that we get that figured out early in the chapter so that you're not lost from right off the beginning. But remember that we're trying to make batteries. We're doing oxidation and reduction reactions, but we're not letting them happen in the same beaker. We're separating them. And the side where the oxidation step, half reaction's happening, is the anode, and the side where the reduction step is happening is the cathode. And then we're going to get electrons flowing through the wire from the anode side to the cathode side. Now, if we think about what reaction is happening on which side, the cathode side is always the one that is higher on this two-column number line. The anode step is going to be the lower number on this chart, but flipped. The reaction will be flipped, so it will be an oxidation reaction instead of the way it's written right here as a reduction reaction. If you flip it, it becomes an oxidation reaction. So then pairing the two reactions, you may have to multiply them by some numbers to get the number of electrons to be the same on both sides, but that doesn't change E naught. Just because you double reaction doesn't mean you double E naught. To get the voltage of the battery that would be expected, if everything is in standard states and standard conditions, all the solutions are 1 molar and all the gases are 1 atmosphere and all the solids are solid pieces of metal, then you can get the voltage by simply taking the cathode, the higher number, minus the anode, the lower number. So E naught cell equals E naught cathode minus E naught anode. Now we manipulate it by reversing the one that is farther down the chart, the anode one. So oxidation instead of reduction, because this chart is all reduction reactions, but you flip one of them to make it the oxidation reaction, and that's the anode number, E naught anode, and the value of voltage that's going to be associated with that particular pair of two reactions is E naught cathode minus E naught anode. Bigger number minus smaller number. So you might have picked up on it by now. Your voltages should be positive numbers. The voltage of a battery is a positive number. Now here's an example where we pair zinc making zinc plus 2 electrons to be the half reaction at the left anode. And actually what you would have is the electrode, the anode electrode would be a piece of zinc, and you would have zinc plus 2 ions in the solution. The zinc plus 2 ions in the solution would be 1 molar. So that's the left beaker. You got your left beaker, which has zinc plus 2 in it, 1 mole per liter. And you have a piece of zinc. Now if we could shrink ourselves down and watch what's happening on the surface of that piece of zinc. That piece of zinc is made of zinc atoms. Zinc atoms are neutral charge. In the solution, very near it, is some ions of zinc plus 2. Now, if those zinc plus 2s come over to the zinc electrode and receive 2 electrons, they can become zinc atoms. But that's not what happens. This is the anode because this is where oxidation is occurring. So actually what happens is a zinc atom is going to turn into a zinc plus 2 ion and dissolve into the water while moving its 2 electrons up the anode and through the wire over to the copper side. So on the left side, we have zinc atoms turning into zinc plus 2 and becoming dissolved in the water. So over time, as this galvanic cell or a type of battery was to run, and as electrons move from left to right in this particular diagram, what we would find is the zinc electrode would slowly lose atoms, which would become zinc plus 2 ions. So it would be dissolving the electrode on the left. If you weight it and then weight it after a minute or so, or it would weigh slightly less because you lose zinc atoms because they dissolve into the water as zinc plus 2 ions. Meanwhile, over on the right, we see the cathode where reduction is occurring. The red cat. So on that side, instead of metal atoms becoming ions, we have ions in the water turning into metal atoms and depositing on the surface of the copper electrode. So the cathode would actually be slowly gaining mass as copper plus 2 ions turn into copper metal and become attached on the copper electrode. And so on the left electrode, the zinc atoms would be turning into ions and dissolving into the water. On the right side, the copper ions would be turning into copper atoms and depositing on the cathode. The anode would be slowly losing mass while the cathode is slowly gaining mass. And notice up at the top, electrons are going to flow from the anode to the cathode because oxidation produces electrons. Zinc makes zinc plus 2 electrons, and reduction uses electrons. Copper plus 2 electrons yields copper. We see the electrons have to flow from the anode side to the cathode side. And to complete our circuit, this particular diagram shows a porous disk that will allow ions to flow from left to right or right to left to continue the flow of electric charge all the way around the circuit. Now, this particular setup, this zinc and copper combination, shows up in the digital voltmeter up there a 1.10 volt value. Now, how do we know that's going to be 1.10 volt? We go to our standard reduction potential table. Now, on this standard reduction potential table, we look for our zinc reaction and we look for our copper reaction. Now, the reaction I want is the one where copper plus 2 adds 2 electrons to become copper neutral. And that is the second row of the right column. So find that on this chart. Copper plus 2 electrons yields copper, 0.34 volts. So that's what's happening on the right side. The blue copper plus 2 is turning into red-brown copper atoms, and that is becoming the solid. And so that's copper plus 2 electrons yields copper. That's a reduction direction. Reduction occurs at the cathode, so we call that the cathode. So now we look further down the chart, because remember the reduction reaction has to be higher than the oxidation reaction. We go further down the chart, and about 2/3 of the way down I find zinc plus 2 electrons yields zinc with a standard reduction potential of negative 0.76 volts. So find the reaction, find those negative 0.76 volts, and let's go back and look at this. Actually, that reaction needs to be flipped, because right here it's written zinc plus 2 electrons yield zinc. We want zinc yield zinc plus 2 electrons, because we want to flip the lower down on the chart value or half reaction and run it backwards as an oxidation step, so that the copper reaction is using the 2 electrons at the cathode, while the zinc reaction is gaining 2 electrons or losing 2 electrons at the anode. So you lose 2, you gain 2. So now if we look at the two numbers, remember the copper was 0.34 volts, the zinc is negative 0.76 volts. Well, if I subtract the negative 0.76, because I'm supposed to do E naught cathode minus E naught anode, if I subtract the negative 0.76, it's the same as adding 0.76. So I have 0.34 volts for one side plus the 0.76, and that adds up to 1.1. If you can't do it in your head, grab a calculator and put them together. 0.34 volts minus negative 0.76 comes out to 1.1 volts. So that's kind of an analysis of this particular type of battery. I'm making a voltage out of running the zinc ion and zinc metal as an anode side, and a copper plus 2 and copper metal as a cathode side. So the electrons are going to flow from the anode to the cathode and produce a voltage measured with a voltmeter here of 1.1 volts. Now with 1.1 volts, maybe I can light an LED or do something. Run a little electric motor or something. But the way we know that's 1.1 volts is we look the two reactions up in this chart. I looked the copper reaction up and ran it forward. I looked the zinc reaction up and ran it in reverse, and then did E naught of the cathode, the forward one, minus E naught of the anode, the one that was running in reverse. Now, notice there is one particular reaction in this half reaction table that has a value of 0.00 volts. So this takes us back to something we've talked about. Certain scales start at 0 and go up. Other scales have a 0 in the middle, like the Celsius temperature scale, versus the Kelvin scale starts at 0 and only has positive numbers. So these E naught values actually are of the type where you have positives and negatives and 0. Now the 0 is usually arbitrarily set. Scientists get together and say, what are we going to call 0? For the Celsius scale, they pick the freezing point of water. For delta H's of formation, we picked elements in their standard states. For standard reduction potentials, the values on this chart, we choose the hydrogen ion turning into H2 gas reaction. So it's the one that's got a little more space. It's over on the right side about 5 or 6 down. 2H plus 2 electrons yields H2 is the half reaction that is assigned a 0 value. So they've chosen the hydrogen ion turning into H2 to be the 0 on the scale. This is what it would look like. Now, because you don't have any metal, H plus is an ion and H2 is a gas, you would actually have to have the H2 gas supplied as 1 atmosphere of pressure, and you'd have H plus ions in the water as 1 mole per liter. And then, in order to have a solid piece of metal that you could attach your wire to, you would use as your electrode a piece of platinum. Platinum is a very noble metal. It doesn't chemically react with hardly anything, and as a result, it could be the metal surface that you would use instead of like this reaction. We used zinc metal because you needed a piece of zinc metal to be the left side of the anode. You need the right side of the cathode to be a piece of copper metal. But in the case of the standard hydrogen electrode, the hydrogen reaction, H plus, that's an ion, that's not a piece of metal. H2, that's a gas, that's not a piece of metal. And so you'd have to get creative with how you create an electrode like that. You'd have to have the H2 gas at 1 atmosphere, and you'd have the hydrogen ions at 1 mole per liter, and then you would choose an inert, we call it a chemically inert electrode, like a piece of platinum. And then we would then connect that wire to the other half cell. And then if we picked one that was below 0 on the chart, then this side would get to be the cathode, and the other side would have to be the anode. We'd flip the other side. If we choose something on the chart that's above 0, then the hydrogen ion reaction needs to become the anode, and the one with the positive number would need to become the cathode. So all of that to say that there is one redox or reduction reaction that is considered the standard and is assigned a value of 0, and it's the one involving hydrogen ions and hydrogen gas. So if we think about it, what's really happening, instead of thinking of it as simply E0 cathode minus E0 anode, and one way I like to think of that, doing that, is simply how far apart are these two numbers on this number line, from positive 2.87 through 0 down to negative 3.05. That's one way it helps me to think about how to find the voltage. But another way of looking at it is we are reversing the oxidation step. As a result of reversing the oxidation step, we're changing its sign. Because if you look at it, the one that you flip is the one that you subtract. You flip the anode reaction because that's where the oxidation is occurring, anox. So you flip that one, and as a result, the anode E value becomes change of the sign, minus E0. So the minus E0 is the changing of the sign. So when a half reaction is reversed, the sign of E0 is reversed or made opposite. But when you multiply to like double or triple the reaction to get the right number of electrons, you do not change E0. So the only change we do to E0 is we subtract the oxidation number instead of add it. Now let's say we had a galvanic cell and we wanted to use this redox reaction. Fe plus 3 plus copper makes copper plus 2 plus Fe plus 2. Now if we look at this as a full redox reaction, we see Fe plus 3 going to Fe plus 2. So that's our reduction reaction. We see copper going from copper neutral to copper plus 2 by losing 2 electrons. That is our reduction reaction. So if we break it into two half reactions, it's Fe plus 3 gaining an electron to become Fe plus 2. And if we look at that chart, that's 0.77 volts. So find it toward the bottom left, about 4 or 5 up from the bottom on the left. Fe plus 3 plus electron yields Fe plus 2. Iron plus 3 is being reduced to make iron plus 2. That's got an E0 value of 0.77 volts, shown right here on the right. Now the other reaction is the copper and the copper plus 2, but the reduction direction would be copper plus 2 electrons yields copper. That's not the direction we want to run. We want copper on the left and copper plus 2 on the right. So this is actually found on the chart as a reduction, because this is a reduction chart. It's found at 0.34 volts. Copper plus 2 electrons yields copper. But since that's lower than the iron reaction, which is 0.77 volts, we'll flip it and make it copper yields copper plus 2 electrons. Now to make this work, by flipping it, we're going to change the sign to negative 0.34 volts. And the second reaction, the iron reaction, the reduction step, we're going to double it to get the 2 electrons on the left to balance the 2 electrons on the right for the copper reaction. E0 0.77 volts. Notice doubling it did not change the value of the voltage. It's still 0.77 volts. And now looking at E0 minus E0 cathode minus E0 anode, or looking at adding them as a 0.77 and a negative 0.34 volts, we find that our voltage comes out to 0.43 volts. The distance between these two reactions, 0.77 volts and 0.34 volts. 0.77 volts minus 0.34 volts, or 0.77 plus negative 0.34 is 0.43 volts. Now the balanced, by adding the two half reactions together, we get the balanced cell reaction to be copper plus 2 Fe plus 3 yields copper plus 2 Fe plus 2. E0 of the cell is E0 of the cathode minus E0 of the anode. 0.77 volts minus 0.34 volts. And so we would expect a 0.43 volt voltage out of this reaction. 0.77 minus 0.34. But that means we flip the copper reaction and run it as our oxidation step. Okay, let's pause here and do a little concept check. Order the following from strongest to weakest oxidizing agent. Now remember, oxidizing agent is based on the ability to be reduced. So, looking at these, which one of these things can be reduced? And remember, some of these may not even be capable of being reduced. So I'm looking at Fe. Well, back on this chart, Fe is only ever neutral or positive. It's never negative. We never add electrons to metals. We always take electrons away from metals. So Fe is one of those things that I can't even put in order because it has no ability to be reduced. Likewise, sodium. I can't reduce sodium. I can oxidize it to make Na+, but I never make Na negative. There is no example ever in chemistry where Na gains electrons. Metals don't gain electrons, they lose electrons. Also, F-. It doesn't make sense to add an electron to F-. F- is an ion where the F atom has gained an electron, and there is no F-2. F- is a full outer shell. It's got 8 electrons in the second energy level. had 7, but then it gained an electron to make a -1, so now it's got 8. You can't put more than 8 electrons in the second energy level, and so F- is done being reduced. It won't reduce further. So your first 3 don't even make sense in this question. They have no ability to be reduced. However, Na plus could be reduced, because Na plus, if it gains an electron, becomes a piece of sodium, an atom of sodium metal, Na neutral. So there's a possibility. I could add an electron to Na plus and make Na. And then the Cl2 also has the ability to be reduced, because chlorine atoms, this happens to be single bonded to another chlorine atom, but a chlorine atom could add an electron to finish its third sp sublevel, S and P sublevels, and it has room for one more, so chlorine can make the chloride ion. So then I go back to here, to this chart, and I look up those 2 reduction reactions. And I find chlorine being reduced about just under halfway down on the left column. Cl2 plus 2 electrons yield 2 Cl minus. You find it? 1.36 volts. Okay, so that means it's there on the chart at 1.36 volts. Now, to find the Na plus electron reaction, I have to go almost all the way to the bottom of the right-hand column. About 4 or 5 up from the right-hand column, bottom is Na plus electron yields Na negative 2.71. So looking at the position of these 2 on this chart, I would say chlorine has a much higher tendency to reduce than Na plus does. And given my druthers, I'd probably, if I combine these 2 reactions, I would flip the sodium reaction, because it's lower on the chart. So to get back to the concept check, I basically would not include the Fe, the Na, or the F minus, because there's no way you can gain electrons on those. However, I might compare Cl2 and Na plus, Cl2 reducing to Cl minus, and Na plus gaining an electron to become Na. But the order would be that Cl2 has the higher potential to be reduced than Na plus. And I gauge that from this chart, because Cl2 being reduced is 1.36 volts, Na plus being reduced is all the way down at negative 2.71. So that means Cl2 wants to be reduced a lot more than Na plus does. Okay, so that's another use of the chart, is figuring out the tendencies to be reduced. So to choose which reactions want to run in the reduction direction, which reactions are more tendency to run in the oxidation reaction. Higher on the number line, higher in the reduction potential chart, more likely to run forward as a reduction. Lower on the number line, lower on the chart, more likely to run in reverse as an oxidation. Okay, so this is our standard reduction potential. Remember, everything is 25 Celsius and 1 molar for any ion, 1 atmosphere for any gas, and besides that, everything is in their standard state if they're liquid or solid. So practicing a little bit more, let's say I want to make a galvanic cell. I want to combine 2 half reactions, one in one beaker and one in another, connected by a salt bridge and a wire, and I want to use this reaction. Al plus 3 plus magnesium make aluminum plus magnesium plus 2. Well, the 2 half reactions would be Al plus 3 electrons makes aluminum. I looked that up in the chart. That reaction is at negative 1.66 volts. Right side, 2/3 the way down. Al plus 3 electrons yields aluminum. And the other reaction would be Mg plus 2 electrons makes Mg. And that's found at negative 2.37. Now, because negative 2.37 for the magnesium reaction is below the aluminum reaction, negative 1.66, I'm going to let the aluminum reaction run the way it's written, but I'm going to flip the magnesium reaction, the negative 2.37. It's lower on the chart, so it has to convert from being the reduction reaction to being the oxidation reaction. So now, if I look at doing the math on it, I would have to double the aluminum reaction. I'd have to triple the magnesium reaction to get 6 electrons on each side. I'd have to flip the magnesium reaction. But when it comes to the E0 values, all of that doesn't really change, except flipping the second reaction would change the sign to positive 2.37. Or another way of looking at it is minus 1.66 minus negative 2.37. When you do that, when you flip the second reaction and change its sign and then put them back together, the combination does end up as a positive voltage. And the numerical value of that is the difference on the number line, the distance between on the number line, negative 1.66 and negative 2.37, which happens to be 0.71 volts. So making a battery using these two half reactions, aluminum plus 3 ion in solution, aluminum metal as the cathode, and then because cathode is where reduction occurs, we see aluminum being reduced from plus 3 to 0. So reduction occurs at the cathode. That would be the cathode. The aluminum metal would be the piece that would call the cathode, and the aluminum ion is on the cathode side of the reaction. Then on the other side of the reaction, we'd have a strip of magnesium to be the solid electrode over there, and then magnesium plus 2 ion would be in the water at 1 mole per liter. And that would be the anode, because remember we flipped that reaction to make it oxidation and ox. Now there is a shorthand line notation that's used to, in a very shorthand method, draw or list the parts of one of these galvanic cells. You start by listing your anode, where the oxidation, the one you flipped. The anode is listed on the left, the cathode is on the right. Now between the left and the right, between the anode and the cathode, you're going to put double vertical lines. That represents the salt bridge or the porous disk. And then if the parts of the anode side, the part that is the electrode and the part that's in solution, those would be separated because they're typically a different phase. They'd be separated with a single vertical line. And the same thing over on the cathode side. You'd have a single vertical line separating the ion or metal that is the two halves. I'm not doing a very good job explaining that, but if you look at this, say the aluminum side where the cathode is, you would separate the aluminum plus 3 ion from the aluminum solid with a straight line, a vertical line. Double line for the salt bridge, single line for separating the two halves of the half reaction that's on each side. You would write the concentration like 1 molar for the aqueous solution if it's standard, and that would be necessary to be correct with your line notation. So if we look at this reaction, because magnesium is where oxidation is occurring, because magnesium solid to magnesium plus 2 is losing 2 electrons, I'd say magnesium solid, vertical line, phase change, solid to aqueous, magnesium plus 2 ion. Double vertical line for the salt bridge, and then on the other side we have the reaction involving aluminum plus 3 ion in the aqueous state and aluminum solid in the metal electrode state. The cell potential is always calculated by just doing E0 cathode minus E0 anode. You may have had to double or triple some of the half reactions to make them balance, but you don't double or triple the E0 value from the chart. The direction of the electron flow you can tell by looking at your half reactions. Your anode is where oxidation is occurring. That side is going to lose electrons. The cathode is where reduction is occurring. That side is going to need electrons to flow into it from the wire. And so generally what we are able to show is that the direction of electrons is from anode to cathode. What might help you remember that is A comes before C in the alphabet. Anode first, cathode second. So electrons begin at the anode but go over to the cathode. So to describe a galvanic cell, you're going to want to know what kind of metal, is it zinc or magnesium or platinum that's being used as the electrode. What is the condition? Is it in gas state? Is it 1 atmosphere? Is it ions? Is it 1 molar of each component that makes up that galvanic cell? If you don't have a piece of metal as one of the two in one of the two reactions, like in this case we have a piece of metal. We have magnesium solid turning into magnesium plus 2. At the anode side, we have aluminum ion turning into aluminum metal at the cathode side. So we have a piece of metal that we can use for each electrode. Piece of magnesium on the anode side, piece of aluminum on the cathode side. But if in some cases, like with the standard hydrogen electrode, you don't have a piece of metal for either part of the reaction, you have to use a piece of platinum or some other chemically inert. So I'm going to pause there and make that the end of this video, and then I will probably be adding some more videos to my YouTube channel besides this one that you should also, but this is a good time, take a break, get a drink, go to the bathroom. We'll take this as the end of this particular first episode of Monday, April 8th notes.